So I will say that number 12 on the homework was a bit trickier than I expected. So I'll make a video just to talk about um, what makes this problem a bit trickier than the other problems that I wrote on the assignment. So let's look at this problem. We have the sum from n is equal to 2 to infinity of sine of n pi over 2 divided by the square root of n. How I like to start these problems is to just write out all the terms. Let's look at what exactly is happening. So we started at n is equal to 2. So I'm going to substitute 2 in for n first. So this is sine of 2 pi over 2 divided by the square root of n, square root of 2, plus sine of 3 pi over 2 divided by root 2, plus sine of 4 pi over 2 divided by, oops, that should be a 3, divided by square root of 4, and make myself some space. Let's do one more term. This is sine of 5 pi over 2 divided by the square root of 5. If you look at this handy-dandy little table or graph that I made on the side, this is the graph of sine. So we see that sine of 2 pi over 2, or sine of pi, would be equal to 0 over the square root of 2. Sine of 3 pi over 2 is negative 1. 4 pi over 2, or 2 pi, is 0. And 5 pi over 2 is 1. So let's look at the numerators. All right, so the numerators, you have this negative 1 over here and this 1 over here. If we were to continue this, writing out all the terms, I think all of you saw that this is going to bounce up and down. This is an alternating series because we bounce from negative 1, positive 1, back and forth. And I saw some of you guys write that our series above is equal to the sum from n is equal to 2 to infinity of negative 1 to the n over the square root of n. I also saw some of you guys say that the sum is equal to n is equal to infinity of negative 1 to the n plus 1 over the square root of n. And in the feedback I said, try writing out the terms for either one of these. So I'll just pick the first one. If you were to write out the terms in the first one, this would be negative 1 squared is positive 1 divided by the square root of 2 plus negative 1 cubed would be negative 1 over the square root of 3 plus negative 1 to the 4th power is 1 over the square root of 4. So we can see that they don't line up, okay? The terms over here don't line up with the terms that we have up here. So we can't say for sure that this series is equivalent to our series above. And you could do the same with the second one over here, and you'll see that they're not exactly the same. But let's look specifically at the terms of our original series. So if I were to write a couple more terms in this series, following the pattern, this would be 0 over the square root of 6 plus negative 1 over the square root of 7 plus 0 over the square root of 8 plus 1 over the square root of 9. So like I said before, you guys saw that this is alternating, and that's great, right? That was kind of like the big thing to notice in this problem, that sine of n pi over 2 bounces up and down from negative 1 to 1, but it also includes these zeros. But let's look at the denominators. Okay, the denominators, square root of 3, square root of 7, square root of 9, the radicand, the thing inside the radical, they're all odd numbers. Okay, all of these even numbers in the radicand of the denominator, they have a 0 in the numerator, so they're not really adding anything to our sum. So the terms that we care about the numerators are bouncing up and down from -1 to 1, and our denominators are odd. So we have to try to write a sum with an a sub n, a thing next to the sum, that is equivalent to what we have above. So we know for sure there's going to be a -1, right? It's going to bounce, it's going to alternate, we need that. We also know for sure the denominator has a square root, right? This is a great place to start, okay? Now let's see how we can change or like add things to our a sub n so that it matches the terms that we have. So let's see if the exponent is just n. So -1 to the n. Let's substitute n is equal to 2 in for n. -1 squared is +1, and we need a -1. So having n in the exponent isn't going to work. But maybe n plus 1 works. What happens now? -1 to the 2 plus 1 power, or 3, -1 cubed is -1. It works out. If I substitute in 3, -1 to the 3 plus 1 power, or -1 to the 4th power, is 1. It looks like we're matching up with what we need. So our numerator is good. This matches up with what we need. Our denominator. We see that our radicand are odd numbers. So one way to express odd numbers is like so. 2n plus 1, right? All odd numbers can be expressed as 2n plus 1, where n is an integer, I think. Don't quote me on that. But, same thing like before. Let's check. If I substitute in 2 in for n, 2 times 2 is 4. 4 plus 1 is 5. So our first term would be -1 over 5, the square root of 5. That's right there, but we don't have this one. Let's try substituting it in n is equal to 3. So 3, if I substitute in 3, the numerator would be -1 to the 4th power, so it would be 1 over 2 times 3 is 6, plus 1 is 7. So the denominator is square root of 7. We have this term, but we're still missing that term. So it sounds like we're close. It sounds like we're close to representing our original series in a new way. But we just have to make some slight adjustments. So I'll say like these are equivalent and this is close. Let's try making a slight adjustment this way. So we're still summing from n is equal to 2 to infinity. Our numerator worked out. We don't have to change anything in our numerator. What about the denominator? One thing I'm going to try is shifting our value of n. If I substitute n with n minus 1 plus 1, what happens now? So our numerator is still the same. So we're going to start with -1. But what happens if I substitute 2 in for n now? 2 minus 1 is 1. 2 times 1 is 2. 2 plus 1 is 3. So the denominator is the square root of 3. Oh wait, I just noticed that our numerators don't match up with our original series. Okay, but they do match up with the original numerators. Okay, let me say that again. That didn't come out right. Our numerators don't match up with the terms exactly, but the order of the -1s match up with the order of the -1s in our original series. So we know that our numerator is good. It's just that our denominator needs work. So back to what we have right here. After shifting our n down 1, our denominator matches up. Let's try substituting in 3. Okay, so -1 to the 3 plus 1 is 1. And our denominator. 3 minus 1 is 2. 2 times 2 is 4. And then 4 plus 1 is 5. So the denominator is square root of 5. And after we continue this process, it turns out that this works. This properly represents our original series. So we can say for sure, after all our lovely work, that sine of n pi over 2 over the square root of n is equivalent to the sum from n is equal to infinity of -1 to the n plus 1 all over, I'm going to simplify the denominator a little bit. That's going to be 2n minus 2 plus 1 minus 1. And I think you guys can finish it from here.